Okay, so good morning, everyone. Welcome back in the second session of this course. The course topic is automatic feature extraction, automatic information extraction. And today we will be talking about pixel-based information extraction. I am Dr. Poonam Tiwari. So yesterday we have talked about what are the basics of automatic feature extraction, why it is required, what are the necessities for automatic feature extraction, why should we go for automatic feature extraction, and what are the different methods. So there are some pixel based methods for feature extraction, there are some object based methods for feature extraction, some sub-pixel based methods for feature extraction. In which situation we have to use which type of extraction technique, that also we have discussed yesterday. So today we will be starting with pixel based information extraction or pixel based feature extraction. So if you remember the yesterday's session, we have discussed that there are various methods using which, or advanced image processing methods using which pixel based classifiers they perform the information extraction. And when do we require the pixel based classifiers? So that also we have discussed yesterday, so we will revise it just within few seconds. That pixel based classifiers will be required where the size of the feature that, or the size of the target is greater than the size of the pixel. So in such cases, we will be using pixel-based classifiers. So apart from using the statistical approaches such as the maximum likelihood classifier, Mahalanobis decision rule, there are other classifiers also for information extraction, and these classifiers can be grouped as neural networks or artificial neural networks, support vector machines. We can also have contextual classifiers in which we take the context of the features, as we have discussed yesterday, that if we want to distinguish between a canal and a road, then canal on the road we will be able to see certain vehicles also, road markings also, whereas on the canal or on the river or on the water body, only the small boats, ships would be visible. So this is by means of association or context we can do the classification of the features. There are certain type of knowledge based classifiers which are decision trees also. So that also we will be discussing today. And the pixel based features such as textures also can be utilized for classification of the features. So one by one, we will be looking at these type of advanced classifiers, which all are clubbed under pixel-based classifiers. So starting with the first one, that is the most important, that is texture. So texture is complex visual pattern which is composed of spatially organized entities that have characteristic brightness, color, shape, or size. Texture, how do we define the texture in a digital image? So texture in a digital image is a function of spatial variation of pixel intensity. That means when we go from one pixel to the other pixel, how the pixel values are changing, whether the pixel values are gradually changing or pixel values are abruptly changing. So if the pixel values are same, the texture would be homogeneous. If the pixel values are different, the texture would be heterogeneous. So there are various parameters by which we can calculate these textures, and various type of textures can be calculated and used for classification of the objects. Okay, so a texture is a description of spatial arrangement of color or intensity of gray value in an image or a selected region of an image. Texture is homogeneous for human visual system. Now, when we are using the visual analysis for classification, we can define the texture as coarse texture, fine texture, we can say that some features are having very high contrast, some are having very low contrast. If there is a regular pattern of DN values, then we can say that we are encountering or we are looking at a regular texture. The texture can be directional also if it is in we are encountering certain lines, certain stripes, then it can be a directional, non-directional. So the rough texture, smooth texture. So we can have so many categories of textures when we are looking at an image visually. But when we are looking at an image digitally, then how do we define the texture? So texture, there are certain properties of the texture. Texture is a property of area because it depends on the spatial variation of pixel values, how the pixel values are arranged in an area. So texture is a property of area. We cannot define texture of an individual point. If there is nothing surrounding that point, we cannot define the texture of the point. So texture involves a spatial distribution of the gray levels. Now, texture can be perceived at different scales also, different levels of resolution also. So you can encounter at very high spatial resolution, very high resolution, you can have a different type of texture. When you reduce the spatial resolution of the same image, you go on resampling the image, reduce the resolution, then there would be the texture would change for that particular area. So texture is perceived when significant individual forms are not present. Texture is usually extracted from a single band of image. So for every band, we will be calculating texture separately. Texture features from different bands of the image are generally different and have different discriminating capabilities of land cover types. Okay, so we have understood that we have to define the texture based on its surrounding areas. We cannot define the texture of one single point. Texture means the how the gray levels or pixel values are spatially distributed, and for every band of the image, the texture would be different. Okay, and why should we use the textures, or what are the different image processing applications in which we use the textures? So textures is used for image classification that I'm telling you about. So based on the textures, you can group an area. Texture can be used for defining the shape of an object. So the 2D image is considered to be projection of a 3D scene, and apparent texture distortions in the image are used to estimate surface orientation in the 3D scene. Texture can also be used to make the objects in the image or segments in the image. So what is image segmentation? It is partitioning of an image into regions which have homogeneous property. So now this homogeneous property can be pixel value, it can be texture, it can be any other property that we defining. So texture, based on the texture, homogeneity of texture, we can partition the image into segments. Or textures can be used for synthesis of certain textures also. So as to build a model of image texture, which can be used for generating the textures. There are a large number of areas or large number of applications in which image textures are used. So it is used in food processing industry to know whether the food has ripened, fruit has ripened or not. So many means what is the quality of the food. Then biometric analysis, the fingerprint analysis, iris, how do you locate a person based on the fingerprint or retina or iris. Then it is used for image processing, used in any sort of image analysis. It can be remote sensing image analysis for natural resource management. It medical image analysis or any type of image analysis, it can be used. It is also used for in GIS analysis, GIS systems also. So the applications of textures are manifold. So how can we create the textures of the from the image, or how can we calculate the textures in the image? So there are basically all the methods for calculating the textures of the image can be grouped into 4 individual categories, namely statistical, structural, model based and filter based. So we will not be talking about any other type of texture features or calculation of texture features, but only we will be doing the statistical method in which general statistical parameters and co-occurrence matrix based features I will be talking about. Otherwise, you can calculate the textures using the filters also. So there are various advanced filters such as Gabor filter. You must have read about these things. Then we have model-based textures in which you can calculate the image textures using fractal features. So many methods are there. So here we will be talking only about statistical method, statistical approach. Within the statistical approach, the textures, there are a certain level of image textures that can be calculated. Either you can calculate the image textures or the statistics only using the digital numbers that are there in the image. So such type of image textures are called as first order textures. Okay, so we are not transforming the image using directly using the pixel values. We will be calculating the texture measures. So this is the first order texture methods. The second order texture methods, which are most commonly used in this, as we have already discussed, texture means how the pixel values are arranged. So in the second order texture measures, the relationship between the two pixels, two adjoining pixels is seen. Means how the variation from first pixel to another pixel is being done. So it measures the relationship between group of 2 pixels in the original image. So these are called as second order texture parameters. Then we have third or higher order texture parameters. They are theoretically possible, but because of the computational difficulty, interpretational difficulty, the third and higher order textures. So most commonly we use the second order texture parameters, and these second order texture parameters are also called as GLCM. If you are converse, if you have any idea about image processing, basic image processing, you must have encountered this term as GLCM textures, gray level co-occurrence matrix. Okay, so we will be discussing the first order texture parameters. So first order texture parameters can be directly calculated from the pixel values or by the histogram. So these are some common first order texture parameters, which are entropy, energy, central moment, and so on. Okay, the formulas are already given here. You need not bother about the formula. The second order texture parameters, or GLCM, is the most classical second order statistical measure for texture analysis. An image is composed of pixels, each with an intensity or a pixel value. Now, the GLCM is a tabulation of how often different combination of gray level co-occur in or an image section. So how a particular combination of gray level occur in an image, in a part of the image. It is also called as co-occurrence distribution. Texture feature calculations use the contents of GLCM to give a measure of variation in intensity at the pixel of interest. So when we are calculating the GLCM matrix, so when we are calculating these GLCM textures, so prior to that, a GLCM matrix is created. The GLCM matrix is a square matrix which has same number of rows and columns as the quantization level of image. It can be calculated at any angle. So suppose we are talking about the central pixel. So from the central pixel, when we are looking, because we are finding out the neighbor of the pixel. So neighbor in which direction? If so, all the directions, all the 360-degree directions are given. So in any direction, you can find out the pixel pair, the neighbors. Okay, and you can create this GLCM matrix, and based on the GLCM matrix, the different features are calculated. The texture features are calculated. So from the original image, as you can see here, from the original image, we have calculated the co-occurrence matrix. From the co-occurrence matrix, we have created the second order texture parameters, these F1, F2 up to Fn. So there are 11 features that can be calculated from the matrix. What are these 11 features? So 11 co-occurrence matrix features are angular second moment, contrast, entropy, variance, correlation, inverse difference moment, sum average, sum variance, sum entropy, information measure of correlation, information measure of correlation second. Okay, so these are the 11 features that can be calculated, 11 textures that can be calculated for one single pixel in the image. Okay, so like this, you can see the input image is there, and these 11 features can be calculated at 0 degree, 45 degree, 90 degree, 135, and so on up to 315, as I have shown you. So you can see that how many number of features means number of information values that can be derived from one single input image. Now it may happen that some of my feature of interest is very pronounced or very distinguishable in the contrast. Some of them are distinguishable in the correlation or variance, some in the entropy. So what we can do is, for different features, we can use different type of, different target objects, we can use different feature vectors and do the calculations and take out the information out of it. Okay. So I'm going to describe some of these second order texture features. So one of them which is very important is angular second moment. It is also called as uniformity. It measures the textural uniformity, that is pixel pair repetition. So how a pair of pixels is repeating. So it detects disorders in texture and energy reaches a maximum value equal to 1. So from 0 to 1 would be the value. So you can see the original image and the angular second moment of the same area. Okay, so many things that are not clear on the original image. Here I have shown the red circles. You can see many features that are not clear in the original image are so pronounced in the angular second moment. Okay, so it gives us further insights into the data set and into the features of our interest. So interpretation on such type of texture measures becomes easier. Okay, then you have entropy. Entropy is the disorder, how much disorder is there or complexity of an image. If the entropy is large, that means the image is not texturally uniform. So complex textures tend to have high entropy. Entropy is inversely correlated to energy. Yeah. So here you can again see the features that were coming black in the angular second moment, those features are having higher values in entropy. Okay. So including all these, you can do the the feature extraction. So then we have this contrast. Contrast is the spatial frequency of an image and is difference moment of GLCM. It is difference between the highest and lowest values of a contiguous set of pixels. It measures the amount of local variation present in the image. So how much contrast is there? So how much variation is there? Okay. So you calculate all these contrast, and then we have homogeneity. Homogeneity is opposite of contrast. It is also called as inverse difference moment. It measures the image homogeneity as it assumes larger value for small gray tone difference in pair element. So where the pixel values are similar, the homogeneity is more homogeneous. Homogeneity. So you can correlate with the term. So homogeneity decreases if contrast increases while energy is constant. Okay, so it is inversely proportional to contrast. Then we have variance. Variance means how much heterogeneity is there, and it is correlated to first order statistical variables such as standard deviation. So in first order, we have seen there is we can calculate the standard deviation also. So it has high correlation with standard deviation. So variance increases when the gray level values differ from their mean. Okay. Then we have dissimilarity. So dissimilarity is also similar to contrast, but the calculation is different. How we assign the weights to different values, that is different. Here we are increasing the weights exponentially. Okay. So these are a few examples. So yesterday I have shown you a case study in which I have shown you how to extract the field boundaries, agriculture field boundaries. So this is, you can see, this is a example how we have used textures for this particular problem. So I have shown you the original false color composite, the data range, the mean, variance, contrast, and dissimilarity have been shown. Now you can see variance also, the homogeneous areas, that means the central part of the field is dark in color. That means it is not showing any it is not showing any variance. It is similar in nature. So dark in color, and the boundary of the field boundaries have difference in pixel values. So the texture is different there, and the field boundaries can be extracted using such type of texture measures. So when we have used these texture measures, we have taken calculated all the texture measures and used different type of texture measures for different type of features, such as what we have observed, that for identifying settlement from its surroundings, the mean, entropy, data range, and homogeneity of some layers are useful. Then for fallow area, the data range, dissimilarity, and variance, all these three were found to be useful. Then saturated dry soil, similarity, variance, and second moment of second layer. Then we have this cultivated area in which the mean layer, mean of layer 3, standard deviation of layer 3, and data range of layer 3 were utilized. Okay, so you can calculate different type of texture measures from the false color composite and use those texture measures for creating a false color composite. So in the lower, you can see the first one is the false color composite of the image. The second one is false color composite of textures that we have calculated. So we have used second moment, dissimilarity, and variance of layer 3 and displayed them in RGB colors, and we have got texture image false color composite. So now you can see many features which were not visible or which were not so identifiable in the original false color composite. They are now identifiable in the texture images. So now you can see how many number of texture measures or texture parameters we can calculate from one single layer. In one you can calculate 11 textures in one direction, and like that you can have 7 or 8 directions. So many amount of textures you can calculate and check your particular feature is visible in which texture measure, and use those in the classification. Okay, so here you can see the yellowish part is all the settlement area. So it is now so clear from its surrounding, and even the agriculture boundaries are very clear. Okay, so using these texture parameters, we have done the classification only using textures. Okay. So now once we have the textures and we have other type of data sets also, how we can utilize all these information to do the classification, and in a manner that a human or a person will do. So there are certain classifiers which we call as expert classifiers, or knowledge-based classifiers, or rule-based classifiers, which can be used for such type of problems. Now, what is the basic concept of image classification? Image classification is assigning pixels in the image to category or classes of interest, such as built-up area, water body, green vegetation. So we have to group the pixels and give them class value. So this is the normal task of image classification, in which we take certain test data, we have some training data, and based on that we learn, we make the model learn, and then apply the trained model to get the results. Okay, so this is how the classification is carried out. Now what are the different image classification methods that can be used? Okay, so this is a table which tells us about what should be the type of classification. Suppose how on what basis should we do the classification of the classifiers. So if the training sample is used or not, then we have supervised or unsupervised classification methods. Okay, so in supervised classifiers, we have maximum likelihood, minimum distance, ANN, decision tree. If in unsupervised, we have ISO data, k-mean clustering. So then whether the second type of classification would be whether parameters such as mean vector and covariance matrix are used or not. So we can have parametric or non-parametric classifiers. Okay. What type of pixel information is used, whether we are going for per pixel classifiers or sub-pixel classifiers. So in per pixel classifier, we have maximum likelihood, minimum distance, artificial neural network, decision tree, support vector machine. So we will be talking about these things. Okay. Then what type of information is used? Are we doing per field classifier or object oriented classifier? So whether the output is a definitive decision about land cover class or not. So in such a case, you can have hard classifier or soft or fuzzy classifier. So in fuzzy classifier, you have fuzzy set classifier, spectral mixture analysis, subpixel classifiers. Whether you are using spatial information or not. So you can have spectral classifier, contextual classifier, spectral, a mix of spectral and contextual classifiers. So these are the advanced per pixel classification algorithms. Okay, so now we will be talking about decision tree classifier or knowledge based expert system. So it is a part of artificial intelligence, which is considered one of very high level classification method to improve the accuracy of the classification. A critical step is to develop the rules that can be used in an expert system or a knowledge-based classification approach. So, main issue is how you are defining the rules for your classification. So, the three methods can be employed to build the rules for image classification. First of all, explicitly eliciting knowledge and rules from experts and then refining the rules. So you take the knowledge and rules from experts and then do the refining of the rules based on your particular application. Then extracting the second method for taking the rules is extracting the variables and rules using cognitive methods, or what we can do is empirically generate rules from observed data with automatic induction methods. So these are the systems or expert system: decision tree classifier, random forest classifier, support vector machines, and ANN. So one by one we'll be talking about these. Knowledge-based systems, they are computer systems which can store knowledge, and using this knowledge it can solve the problems like humans would have solved. Knowledge-based systems are AI programs with program structure of new type, which has knowledge base and inference engine. The basic characteristic of knowledge-based system is that it is an intelligent information processing system. It is a representation of domain of interest. So, and it is not just any system, but it tries to solve the problem by symbol manipulation. Okay. So suppose you have means there is a user, and using the inference engine, it generates a knowledge base which will be used later on for doing a problem solution. So now how are we defining the rules? Rules are generally made using an if then else condition statement. So we are simply doing if then else condition. If this is true, then what should be performed, what should be the action, and if the condition is not met, then what would be the action. The condition portion of a rule statement is a fact that pixel, suppose we will be talking about it, how the conditions are generated. Okay. Now, how we can create the conditions. Suppose simply we can say that if there is a pixel which is having such type of condition, that if in the blue band the reflectance is less than 15%, in the green band reflectance is less than 25%, in red it is less than 15%, near infrared less than 45%, then we can say it is a vegetation pixel. You can see, or we can give the pixel values. And that pixel value range could be this and this and this and this. Then what would be the solution, or what would be the answer? Okay. So in a decision tree, there are root node and the leaf node. So a decision tree takes as input an object or situation described by a set of properties and outputs a yes or no decision. Decision tree therefore represent Boolean function. Functions with large range of output can also be represented. Such as if you are saying if you want to decide whether you will go out to play tennis or not. So how are you going to decide that? So first of all, you will check how is the weather. So whether it is sunny, whether it is overcast, or whether it is raining. So if it is raining, definitely you cannot go for to play. Then if it is overcast, then again, how much is the humidity? That also you can check. Or what are the chances of rain? That also you can say check, which you can decide whether you want to play or not. Then if it is sunny, then you can sunny, yes. Then next would be whether the humidity is high or normal. If the humidity is also normal, then you can go out for play. So this is how we take decisions in our day-to-day life. So same type of decision making when we put into our computer system, and at every step we are having a very simple question based on the for which the answer could be yes or no, and based on that answer we will pose another question, and like this you can go on making leaf notes till the time you conclude on a particular decision. Okay. So you can see that each internal node tests an attribute and each branch corresponds to an attribute value node. Okay. And each leaf node assigns the classification. So a type of multi-stage classifier, a decision tree is a type of multi-stage classifier that can be applied to single image or a stack of images. It is made up of series of binary decisions that are used to determine the correct category for each pixel. The decisions can be based on any available characteristics of data. Example, taking an elevation image and two different multispectral images collected at different times, and any of those images contribute to decision within the same tree. No single decision in the tree performs the complete segmentation of the image into class. So just by having one single question or any one decision, you cannot finalize the class. So small steps are taken and final classification is done. Instead, each decision divides the data into one of two possible classes or group of classes. So this is how, suppose we have to decide on or classify the a particular tree species, which is white fir. Okay, so and we are using this thematic map per image. So what we do is we can have multiple rules. So if you start from here, you can see in the multispectral image we have calculated the NDVI. So first of all, we have to check whether the NDVI is greater than 0.2, less than 0.7. So if that is true, then it will check another means this should be true. Then the value in band 5 should be less than 47. TM band 5 should be within 19 to 47. Band 4 should be between 30 to 86. Band 3 should be 22 to 32. Band 2, 31 to 41, 44 to 51. Like this, you have created these rules, okay, from the multispectral. If these all should be true, then because this particular species will be found only between a slope of 25 to 50 degrees. So the slope image also would be considered. The slope for that particular pixel should be between 25 to 50 degree. The elevation because at a particular slope, at a particular elevation, and greater than 1900 should be the elevation. Then aspect also 0 to 45, and this is elevation and aspect. Okay, so all these, when means all these conditions are true, these are our rules. So this is the sub-hypothesis, conditions, and finally we will say, based on the pixel value, based on the habitat conditions, based on all the knowledge that we have, we can decide that this particular pixel belongs to, or the vegetation here is for this particular species, that is white fur. Okay, so this is how the hierarchical decision tree classifiers are done. Okay, similarly, you can see, you can have another conditions. Okay, another set of images, another set of data, you can have other set of conditions. So like this, first of all, you should know what I want to classify. If I am doing it manually, what should be the logic, what should be the rules that I will form for classification, and then finally transfer those rules, create a hypothesis, make the rules and make the conditions in the decision tree. And based on that, you can do the classification. Okay, so you can see this is another one. So they have taken the ratio of the band 4, shape index, so many things, means you can add up all these, add up all the parameters. So we have discussed about the pictures, you can take ratios, you can take any type of information and make the rules out of it. And no need to have only one single rule. Like you can see, they are making rules for NDVI also, they are making rules for band 4 value, for slope value, and so on. You can see, they have seen that NDVI should be greater than 0.3. If it is yes, then check whether the slope is less than 20 or not. Okay, so if it is less than 20, so whether it is in north or not. So likewise, you can go on classifying from class 1, 2, 3, 4, and 5. Okay, so you can create your own logic. Now, what is the advantage of expert systems or knowledge-based systems? It makes up for the shortage of experts. It spreads the experts' knowledge. The field of interest changes are well tracked. So it increases the expert's ability and efficiency. It preserves the know-how, means the classification is not just based on statistical parameters. It is based on the actual logic also. It can be developed systems and really consistent in advising, equable in performance. They are available permanently, able to work even with partial or non-complete data, and able to give complete explanation about the data. So what is the disadvantage? Because their knowledge is from a narrow field and they don't know the limits. Because then how many set of rules are you going to incorporate into it? The answers are not always correct. The advices have to be analyzed. They don't have common sense. All of the self-evident checking has to be defined. There are many exceptions. You can increase the size of knowledge base and the running time. So this random forest classifier is an extension is a type of knowledge-based classifier. Now you can see we have created a tree-like structure in decision knowledge-based systems. So in random forest classifier, instead of having one single tree, you are having multiple trees. So it is an ensemble classifier. That means a combination of different classifiers which uses multiple decision tree models. It can be used for classification or for regression. The accuracy and variable importance information is provided with the result. A different subset of the training data are selected with replacement to train each tree. The remaining training data are used to estimate error and variable importance. So overfitting is not a problem. Accuracy and variable importance, because why overfitting is not done? Because we are creating the or we are checking the answer from multiple trees. So it is like that you are giving a question to 10 people and all of them come out with their solution. So, and then at the last you vote whichever is the maximum number of people they are getting that answer, you are going to use that as answer. So it is not very sensitive to outliers in training data, because the same training data is used by multiple trees. So you can see this is how a decision tree is created. Actually, each node in choosing the split feature, create decision tree from every sample, take the majority vote and do the classification. So here I have done a random forest classification and a maximum likelihood classification, and what we have observed, many features which were not clear with the maximum likelihood, they have been classified very accurately using random forest classifier. Then next one is support vector machine. Support vector machines are also new generation of learning system based on the statistical learning theory. It delivers state-of-art performance in real-world applications such as text categorization, handwritten character recognition, image classification, biosequence analysis, etc. These are supervised learning methods. The SVM algorithm builds a model that can predict to which class new data point will belong. The separate category or classes are divided by a gap that is as wide as possible. The support vector machine constructs a hyperplane in a space that has high or indefinite dimension. For a good separation, the distance from training data points of each class of hyperplane should be maximized. So suppose these are some random pixels. So what it does, it categorizes the class in the training data. It categorizes the class A, class B, and how you can create a plane between class A and class B so that you have maximum distance from class A and maximum distance from class B. So this is called as, because this plane is constructed in a n-dimensional space, hyperdimensional space. That is why it is called as a hyperplane. And the pixels which are nearest to this hyperplanes, they are supporting this hyperplane, so they are called as support vectors, and this classification method is called as support vector machine. The next one is artificial neural network. It is an artificial system that could perform intelligent tasks similar to those performed by human brain. So human brain, as you already know, it is made up of, means how the brain is transmitting the signal is through the neurons, large number of neurons which are all interconnected to each other. So the same concept is taken here also, which takes the which copies from the human brain, large number of neurons are there, electronic neurons are there, and all these neurons are means these neurons are very simple processing units, but the important point is that they have high degree of interconnection. These neurons are highly interconnected to each other, and it transfers message from one neuron to another. And in between, it does some calculation and creates, does the calculation and transfers those messages to the next layer of neurons. So generally in our neural network, we have an input layer, we have an output layer, and in between we have 2 or 3 or more number of in between layers, which we call as hidden layers. So there can be no or some hidden layers in between. So these neurons are highly interconnected processing elements in one layer, which are connected to all neurons in the next layer for passing the information. Neural networks learn by example. The disadvantage is that because the network finds out how to solve the problem by itself, its operation can be unpredictable. So how does the ANN work? First of all, we have to train the network. During the training of the network, the input training sites to the network are provided. Network computes the output. Then it compares the calculated output with the desired outputs, and based on the difference, the weights of the connection between different neurons, they are adjusted so as to reduce the error. Now, once the network is trained, we can use this network by using another set of input data. The network computes the output based on the training that we have already provided. Okay. So this is an example of a complicated neural, complicated ANN. So